Hello, everyone. My name is Yizo. I'm a research scientist from Intel Labs.
Hi all, my name is Arun Raghunath. I'm also a research scientist in the labs at Intel. And today, the topic of our talk is decoupling SDS architectures for agility. So to begin, I'll just start by giving some context of this work. So over the last couple of years, we have been working on this area, and it kind of falls under an umbrella of making the case for decoupling SDS architectures. So in the past, we have illustrated what SDS decoupling means via control and data plane separation. We have done some POC work on Ceph using SPDK and in the NVMe over Fabric ecosystem. And we gave a talk on this in 2018, where we demonstrated the benefits of decoupling when storage is physically disaggregated. When you physically disaggregate the storage from the SDS server, you actually encounter extra data hops, which increases latency and bandwidth consumption. And this talk in 2018, we spoke about how decoupling helps you to eliminate that extra hop. Last year, we gave some benchmarking results on this POC, and we also described how decoupling helps you in a few other vectors, namely scaling out of multiple heterogeneous storage services. You also get benefits to recovery and separation of failure domains. And it also eases the integration of next generation storage and mixed media types. And we'd like to point out that another colleague of ours is giving a talk on this topic, integration of next-gen storage and media. The topic title is Mortimer, so please go and check that talk as well. Now, with that context, all around decoupling, the focus of this talk is on agility. What we're talking about is that agility needs to be considered in SDS architecture design. We'll describe what we mean by agility, why we think it's needed, and what SDS must do, or how SDS architecture should evolve to handle agility. And again, we'll make the case that decoupling the SDS architecture helps agility. So without further ado, I'll jump into this now. So why do we think that agility is needed in SDS? Mainly because there's an emerging set of workloads which are elastic and dynamic in nature, and they place new demands on storage. So one class of such applications is those that are based on the serverless computing paradigm. So in this paradigm, basically, there's a massive scaling that's possible based on event triggers. And when this happens, when application components scale out massively, they demand high throughput from storage services. And this happens in short bursts. And this kind of behavior, demand for high throughput in short duration bursts, is something that SDS must address to meet these applications' demands. Another class is AI ML workloads, video analytics pipelines, and these have characteristics where they demand low latency access to storage. They demand performance boosts for subsets of data. And again, SDS must meet these needs. Another class is the very popular microservices based design, where you have pipelines or even graphs of microservices that are chained together to build a complete application. And these applications desire efficient data movement as well as efficient storage capabilities. SDS must meet these needs as well. Finally, mobile workloads, emerging edge workloads, all of which are inherently dynamic in nature, require low latency from storage. And typically, this is viewed as being possible when you deploy these services closer to the client. So again, SDS must meet the needs of all these sorts of applications. Hence, we say agility is needed in SDS. Okay, what are the bottlenecks currently, which makes us think that this need of agility is not met by current architectures? So SDS architectures are really good with respect to offering scale out on the vector of capacity. So there are lots of designs out there where you can add nodes as you desire more capacity, and this works really well. But adding a node in order to meet the agile demands of elastic applications is not really met by this knob, if you will, because this is orders of magnitude slower than what the application needs. There are no scale out knobs for short duration bursts. One might say, hey, if I know what the worst case burst is, I can over provision. But if these worst case bursts are for only short periods, over provisioning is too costly. So that's not an option either. The other aspect is if you scale out when load increases, there needs to be a means to scale down as load reduces as well. So again, there are no mechanisms to do this efficiently in SDS currently. And finally, you can't have subsets of data for which the framework boosts performance currently in SDS architectures. So these are all the bottlenecks that exist currently. And we believe this is a difficult challenge to go past in current SDS designs, because the software stack is monolithic, it's deeply coupled and closely integrated. Another aspect is if we say, hey, somehow I can add and remove nodes really quickly, you encounter this other issue where data is rebalanced within a cluster. Now note that this is by design. The intent there is to make sure the data is uniformly distributed so that no one node experiences overload. But for the kinds of applications we are talking about, dynamic applications where for short duration performance boosts are needed, if when you try to meet that need by adding nodes, if there is an increase in background traffic because of rebalancing, that just defeats the whole purpose of adding the new node. On the topic of background tasks, for the high durability guarantees of SDS, a lot of background tasks like scrubbing and the rebalancing that I mentioned is done. And these have a global impact on the foreground application performance. And so these are the kind of challenges that currently exist in SDS. So given these challenges, the question we pose is, can decoupling allow you to enable agility in SDS? And to make this happen, we believe the following mechanisms are needed. You need to be able to dynamically add and remove resources. And this addition or removal should be triggered based on load. We want to be able to offer performance boosts for subsets of data, regardless of where that data is in the entire cluster. And most importantly, when these resources are added or removed to respond to load, it should not trigger a data rebalance. So in the rest of this talk, we basically examine if decoupling the SDS architecture will allow us to provide these mechanisms in SDS.
So we believe decoupling will help, particularly design the SDS towards a direction that will satisfy the agility needs that Arun described earlier. But before we go into that, let's just have a brief revisit of what we have done in the current decoupled architecture work that we have presented in the previous SDC talk. So in our decoupled SDS architecture, we basically separate the control plane, which is the top half, from the data plane, which is the bottom half. And on the top half, it performs a cluster-wide operations, such as deciding how to place a data placement strategy to your final destination to satisfy your required SLA. and manage replicas or recoding chunks, deciding where they're going to add it. And also monitor the data integrity, meaning that if you have actually from your scrubbing, if there's a data integrity problem that is being identified, that will be recovered by the top half. And also perform the failure recovery logic, meaning that if you have a node that is gone due to some reason, it will be able to bring that back or have a new node added to make sure the whole cluster is still back to the healthy state that it is expected. On the other hand, for the bottom half, it is responsible for actually storing the data and metadata. And it essentially is guaranteed the durability aspect and provides persistence for your data. It's somewhat in a similar manner like a file system. It maintains the block layout. So eventually where the data blocks for your objects are located are sort of managed through that bottom half. It also supports transactions, provides object semantics operation in the over fabric. Our current POC have a standard-based fabric to communicate between the top and bottom half components. And particularly, I want to point out that our decoupled architecture is designed to apply to both hyperconverged as well as desegregated deployments. As you can see, we have sort of these two example pictures here. On the left is a hyperconverged scenario. On the right is a desegregated scenario. Regardless, the decoupled architecture, because of the two components are essentially separate from each other, they can be independently scaled with more flexibility that actually is applicable to both hyperconverged scenario as well as desegregated deployment scenarios. So in the case of the agility for SDS, particularly how do we leverage containers to deploy our SDS components that will essentially to play towards the benefits of those emerging workloads that Ron described earlier. So we can see with the decoupled top and bottom half, they can be easily put in the containers, and that will enable quick bring up and bring down of these two SDS components. And because they are sort of separated or decoupled from each other, their scaling out factor is completely independent from each other. You can clone the top, bottom halves based on their own pressure or demand from wherever they see. You can have multiple tops for one bottom, or you could have the other way around. You could add or remove clones where needed based on your actual load. And this is also leverage the MEMR fabric between top and bottom halves, which will enable communication even when SDS components are on different nodes. The bottom part is a picture that we did for our previous work in SDC18 as well as SDC19. And the left side is particularly illustration of how we realize this using Ceph as a study case. And you can see on the picture with Ceph OSD, we have the top half data, the control plane still maintain the same functionality that it was designed to do. And also on the right side, which is the bottom half, responsible for actual persisting the data to the storage devices. There's some more details of how our implementation, but this is just a revisit. So I'll just leave to the audience. If you have more questions, we can follow up later on that part. But more importantly, what are the challenges in managing the agility in SDS containers? So if you think about how SDS actually work, you want to ask yourself, if you want to really achieve that kind of dynamic nature, as we pointed out those emerging workloads, how do you avoid data rebalance when you have a clone come and go? And this is essentially in the same scenario. You have OSD coming, you have to add OSD. If you have a disk going away, you want to add a disk, you want to actually add OSD, or disk failure, you want to remove OSD. Essentially, it's going to create a rebalance, but that's not what we want. That's our design goal, is to avoid that as much as possible. Actually, absolutely have to avoid that. Another part is a location challenge. Now, you have the clone, but how do you map your object to where the clone is? Because the clone, as we said, we want to avoid data balance. So you have to have a mechanism to map your object to your actual clone node. That client will be able to direct IO request to the clone. And another part is about cache consistency. Now think about the object has been placed into the cache node. Now, if there's an update coming to that object, what are you going to do? Essentially, you have to face the problem of you want to still serve using your clone to the client request, but you want to serve the actually most updated contents. So how to keep your cache data current in the face of updates? So this is another challenge we're trying to solve. And we're going to show how we have some proposed solutions to solve these individual challenges. And we start by first one, the rebalance challenge. What we propose here is a novel approach for the agility part, particularly targeting and rebalance challenge. So one aspect is when we clone the top OSD, we want to place the data close to where it is actually needed. That means we can scale out the OSD's rate throughput as much as we want. At the same time, this should not contribute to object placement. So in the context of Ceph, it does not really play part of the crush, which takes the topology and decides where the data needs to be finally persisted on the durable device based on your policy of either 3 replica or 5-2 area coding profile. It also functions as a cache node. As I said earlier, it does not require a durable backend, meaning that gives us a lot more flexibility that when you have a container management framework, if you have free resources and you want to scale this up to satisfy your client node, you can do that without worrying about you have to have a durable backend there for you. This is also fundamentally different from tiering because it is working in a different mechanism. It doesn't really provide sort of a cache tier pool as what Ceph has in cache tiering. And it is also working on a per OSD load level to address issues coming from the clients, particularly creating a lot of pressure to the OSD. To solve that, we also introduced this concept called clone map as part of the cluster metadata. And the clones are tracked as part of this clone set for a given OSD in the clone map. And this is definitely separate from the current existing design, like the crush in Ceph. It's not related to your SA policy on persistent data for satisfy certain availability, like 3 copies or 2 copies. So we're going to describe more details on how clone map is used later. Let me continue on the bottom half. So imagine the scenarios you have targets already deployed, but now some targets are facing a bursty write or some sort of pressure on the target. But the OSD can actually do more work there. Now, OSD is essentially being limited by the bottom half because it is receiving a lot of pressure. This is where you can actually leverage clone OSD bottom half to solve that problem. And it is completely transparent to every entity in the cluster except the fronting OSD top half. This is also the benefit you can see coming from the decoupled top and bottom half. And the OSD top half independently removes clones based on the load that will actually can take care of both the load from the front side, the client side, or the backend on the target side. In a nutshell, decoupling enables adding SDS clones without data rebalance and does not cause any object migration across failure domains. And this would achieve our problem of the rebalance challenge we pointed out earlier. Now, next challenge is a location challenge. So how do you particularly meet the client's IO demand? And this first part is handle the location challenge, looking at the clone of the top half. So Ceph itself uses a crush to do a mapping of the object to the final destination of the OSD. And if there's update when you add or remove OSD, that crush needs to be updated to reflect the fact the OSD is taking is playing a role there. If you look at the picture on the right, this is how we try to illustrate how the clone map works to help the information of the clone set for OSD to be delivered to the client side to allow the client to find where it should go, direct its IO go to. If you have an IO request coming as a get for a full object, in the current case, you can look at the crush map, finds out where is my actual OSD is. In this particular scenario, it's actually going to be OSD2. And OSD2 is a primary for this full object. In normal case, this IO request will be delivered to the OSD2 to retrieve the full. Now, in our case, we have a clone map as part of the metadata. The client would actually consult, check the clone map, and it will see actually there is a set of clones for OSD2. And in this particular example, it has 3 clones, 1, 2, 3. And one of them has the full cached. Of course, client doesn't really know which one actually has a full cache there. What we are thinking is to actually drive agility part, we propose sort of a multicast based approach here. The important part is the client knows the clone set. It actually can just tell all the clones in that clone set that I want this full. Whoever has it, just let me have it. That's how it works in what I refer to as the multicast. We believe that is going to scale very well with as many as clients as possible. And the GET request is small enough, it produces as little as overhead in the multicast. And the metadata is tracked by the clone map. When you add or remove a clone, the metadata is getting updated and doesn't really create any consistent issue. Even for the worst case, your clone 2 is somehow removed, added. When you say there is a clone that has the data, it's going to be a miss. Eventually, you will still get your data from your primary OSD. That's the worst case. So this works seamlessly with existing cluster, meaning it doesn't really create any side effects to the existing operation that are going on. In this particular example on the right side of the picture, you can see it's basically say whether OSD clone is empty from the clone map, and if it is there, then it's a hit, or if not, it's a miss. In summary, this enables scaling out of client rate throughput from individual OSD that actually achieve the purpose of the location challenge, particularly meeting the client's IO demand.
Okay. Now, the second aspect of the location challenge is if you've actually cloned out the bottom halves. So again, we do this when a top half notices that the original target to which it was sending its request is facing some pressure, it's not keeping up. And specifically, we are focusing here on the short bursts of writes that might occur. And when that happens, the top half can choose to add new clones to assist the original bottom half. So a few assumptions before I get into how we locate the right place to write. We assume that clones can come and go as needed, that they exist for short durations. And given this, a majority of the objects we expect will be located on the original bottom half, right? The bottom half clones are only there to assist briefly when the original target is overloaded. So with those assumptions in mind, how does the OSD top half handle a write if there are clones, right? So firstly, the top half is the entity that initiated or made these extra clones. So it has the information of which clones these are. And in fact, in our decoupled Ceph POC, we had introduced a data structure called target map, which includes information about where the targets are. So it is at that level where this information about a target's clones are added. And the reason I point that out is this is transparent to all the layers above. It's only the OSD top half that knows that, oh, my target was facing pressure, so I've created some clones. Okay, so now clones were created, and now a new write comes in. So when a new write comes in, the first thing the top half will do is it'll choose amongst its original or clone targets. And let's say it chooses a clone. At this point, the object URL will be added into a Bloom filter, which is basically used to track all objects stored on all the clones for this particular target, right? We use a Bloom filter because it's known to be a scalable data structure. And really, the only kind of decision point for the top half is, whether it should write to clone or the original target. Once it has chosen this, it has added an entry into the Bloom filter. In round robin fashion, it will pick one of the clones and write the data there. Okay, so we have written the data on the clone. Now a read came in for this newly written data. So the top half will query its Bloom filter. And again, recall that Bloom filters will not give you false negatives, right? So if the data is present on the clone, then it will, or rather, if it is not present on the clone, if it is present on the original, then you will get that information correctly. So if the Bloom filter says it's not found in a clone, and this is more likely because most object requests will be met from the original target, you send the request to the original target like before. If the Bloom filter says it is on the clone, then we multicast the read request to all clones of this target. Again, the same caveats that Yi mentioned earlier. This scales because the set of clones is small, and this is only limited locally between the OSD top half and its set of clones. Now, with Bloom filters, there is a possibility of a false positive, in which case the Bloom filter indicated that the object is present in one of the clones, but it's actually not there. All this means for us is if we don't get any of the clones responding to the read request, we can then fall back on the original target and the data should be there. So that's how we kind of propose to handle reads and writes. Now, the last part that remains is how do you handle reduction in load? So the OSD top half will see that the write burst is done. The original target is keeping up easily. And so at this point, it wants to reduce the load. So the first thing it needs to do is choose one of the clones and issue a command to kind of copy off all the data that was written temporarily on this clone to the original target. And once all of the data has been written, that clone can be shut down. This is done for all the clones. And once all the clones have been removed and all the data has been copied off to the original target, we can basically reset our Bloom filter, and the cluster state is kind of the same as how we began before this write burst. So this is how we think we can solve both the challenge of scaling out the write bandwidth of the bottom half of any OSD. And we can enable finding out where actually to write and where to read from when clones of the bottom half exist. Okay, now the third challenge that Yi mentioned that we have identified to handle agility is that of the cache consistency challenge. Now, before I go into this, I'd like to just do a revisit of a feature that we had added for our decoupled POC, which we actually take advantage of here. So this feature is that of remote asynchronous transaction, which we implemented in our decoupled Ceph POC. Now, the details of that are kind of shown on the picture on the right. It's a little bit of an eye chart, and the intent is not to get into the details of this in this talk. If anyone is interested, feel free to reach out to us. We can share more details on that. But the main takeaways of that implementation is that the top half can issue transaction requests to a bottom half even when it's remote, as in on another node. And we have enabled asynchronous completion notifications from that remote bottom half to the top half. This asynchronous completion mechanism was crucial for us in the decoupled Ceph POC for ensuring high throughput. Another concept that we had to introduce was that of cohort notifications. And basically what this means is a transaction from a top half can be submitted on behalf of other top halves. So one OSD can actually submit a transaction on behalf of another OSD. And we do this by essentially adding some information in our transaction request that is sent over to the bottom half, namely the list of OSDs that are interested in receiving a notification when this transaction completes. The original goal for this was in a disaggregated scenario to avoid or eliminate the extra data hop that would otherwise be required when a primary OSD which gets a new write has to replicate it on one of the peers. So this cohort notification technique allowed us or allowed the primary to write directly to a peer's target and indicate that the notification must include the peer OSD. So now coming back with this background to our cache consistency challenge. So basically we said we can clone top halves to meet the high read throughput demands on the top half. So the picture here on the left is showing that we cloned a top half, and after that cloning, some object foo was cached on this cloned top half. The consistency issue that we refer to is after the cloned top half has cached some object data, if a new write request updates that data, right? So here we're showing the top half is getting a write request. And remember that we are not messing with clones in the write path, right? So writes are always sent to the original top half. So the original top half is the one that will issue the write request to the bottom half. Whether it's on the same node or remote is irrelevant for us because our mechanism supports both. And in this object write transaction request, the top half, since it knows what its clone set is, it will include the list of all the clones that need to be notified. The simplest is where it includes all of the clones, basically. So what will then happen is when the bottom half actually completes this transaction, it will send this completion notification to not just the top half that initiated the write request to update the data, but to all the clones of this top half. And this allows that clone to then pull up the latest copy of the data. So essentially, cohort notification that we introduced in our remote transaction support in the decoupled Ceph POC that we created, we think will allow us to keep cached data on cloned top halves to be in sync with the actual persisted data. So with that, we have essentially kind of talked through all the three challenges that he mentioned before. So now let's put everything together just to give an end-to-end view. So here we're showing a cluster of Ceph OSDs, which have where the OSD has been decoupled. So let's say the top half is experiencing pressure. So it clones itself. And so we are now showing the clone that's added, and a clone map for that OSD gets updated with this new clone. So now when some client issues a GET request, that GET can be answered by the clone. And going forward, that data is cached on this clone. There's another scenario that we'd like to point out, wherein we have introduced a mechanism whereby when a new clone is created, we can also essentially pre-populate its that clone or warm its cache. whereby you can specify a batch request of objects such that when the clone comes up, it's instructed to just go and pull out from the bottom half this list of objects. So that's what we're showing here, where this clone was instructed to pre-populate the object bar. So when it came up, it already has it cached. So when a client that requests this object bar, when it makes a request for it, it will be answered by the cached copy directly. So this is just a means to reduce latency, which we can take advantage of in our decoupled approach. And then the third part is where we are showing, the blue store bottom half here is experiencing pressure, which is noticed by its corresponding top half, OSD.1. So it spawns off a clone, and when it does that, it has created the required metadata to track that there are now 2 clones available for it. And when a new object put arrives, this OSD can choose not just the original, but it can choose to go to the clone that it just spawned off. And it decides where to go using the Bloom filter approach that we described earlier. And so by doing that, it can reduce the pressure on the original bottom half. Okay, so essentially, we think by doing this decoupling, we can clone top or bottom half by avoiding cluster, while avoiding, I should say, a cluster level rebalance. We described how with clone maps for the top half and a Bloom filter and round robin lookup for the bottom half, we can locate where the objects actually are if they are present in one of these dynamic clones that come and go. And finally, we spoke about how cohort notification that we introduced for our remote transaction support in the decoupled architecture lets us keep the data updated even if it is on cached on one of these clones. So yeah, that's how we put all these together.
So now I hope you guys will have a very good idea of the advantage of this proposed approach, at least I hope. And just to reiterate that this proposed approach has some unique aspects of advantages. And you can see already the first goal we want to see is a scale up and down with minimal overhead. The decoupling allow us to do that. That's why we actually reinforce that the decoupled architecture is the foundation for this work. And the clone OSD can be started with the intelligent warm-up cache. That's what Arun just described. If you actually can have that information, that will be able to actually support that usage model. This is particularly useful for this newly emerging fast-like pipelined microservices, which have become more and more important nowadays. Clone OSD can also directly pull batch objects from the targets or other clones. And you can see from the previous example, we do have that capability. The clone itself can talk to the backend targets. And particularly on the right side, when you have a target that is sort of unbalanced, receiving a lot of pressure, and that I think is one particular area not many existing literature has already looked into that aspect that we are hoping solve. You can actually scale the right throughput by creating some clones for your target that will particularly handle the bursts, and I think that will be a good approach to this particular problem. And I would also point out that updating clone map is likely to be more frequent than others, which is sort of expected, particularly comparing OSD map when you add an OSD which actually has a durable backend, where this front clone OSD is designed to come and go as frequently as possible. But by the mechanism that Arun and I described earlier, we are pretty sure that it will actually be able to handle that kind of dynamic nature without impacting any of the existing cluster behaviors. The target clones are only visible to corresponding top half. So essentially that means the target itself can be cloned, but it's still going to be responsible for its pure top half OSD. And that lifetime is also controlled by that type of OSD because it's designed to help that particular target which is under pressure. Another part is, I probably mentioned that a couple of times, that there are no side effects, no rebalancing, and behaves as a recache miss, even if you cannot find that from the clone map. And clone is now removed till the clone map is really updated, so you don't have run into that inconsistency issue. Two other aspect is we want to at least share some of the thoughts we are going through. One discussing point is, how does this kind of work or compare with existing containerized SD solutions? We already know there are prior art for SDS containers in the space, like Mini.io is already a cloud-native SDS solution. Rook.io is a very good framework using container to manage SDS services. And there's publications like the one we reference here, looking particularly at how to containerize Ceph-OSD. But we have to point out these work all focusing for different goals. The entire monolithic SDS stack is still containerized no matter what in these existing efforts, which basically means you cannot scale bottleneck components independently. You still have to solve that issue. And the focus is really on the ease of the management. So it doesn't really help on the dynamic IO demands from the clients. Another part of the discussion point I want to bring out is the existing caching solutions. We know there are client-side caching like web cache or Ceph RBD, RGB, Reader's Gateway also have caches. But these are ineffective for clients with high mobility and pipeline microservices particularly. You also require additional support on the client platform, either hardware or software. It is not really helping at a per overloaded OSD level. That's another aspect. On the other hand, you have storage node cache, which typically is a block level cache like Bcache or flash cache. It is a per block device, so it's not exactly designed for a client-oriented manner. And you also have to deploy the cache device for all storage nodes, otherwise you have an unbalanced behavior. The memory-based caching framework like Memcached or Redis, there's a separate mechanism that require you have a separate management piece as well as investment on the software as well hardware infrastructure. Tiering, similar manner, is designed to actually have you have a multi-tier with fast meter you can go, and somewhat back you move to the slower meter. Particularly, this is very complicated as exemplified by the Ceph-cache theory design, which is fundamentally another storage pool, but to be designed to be put on the faster media. And fundamentally does not meet the agility requirements that we explained in the beginning of this conversation. So to sum up, the emerging workloads that we pointed out earlier, they all demand high agility from the storage side. And how do we help this SDS architecture design to achieve that goal is what we want to solve in this particular talk. And we believe decoupled SDS architecture will make them agile. And independently clone control and data plane, clone the data plane and control plane via containers because of the decoupled architecture will allow you to achieve that end. And you can scale based on the load with no cluster level rebalancing. Particularly, it's transparent clone bottom half under right pressure, or you can clone top half to reduce latency. Gives you as enough flexibility and scalability as you want. For the next steps, we want to complete POC to support clone OSD and clone map using Ceph. We also want to evaluate scaling capability with dynamic clients and pipeline microservices. For this talk, we want to call it out that we make a case for a decoupled SDS architecture. And particularly, we want to say in our previous work, as we showed you guys before, we have achieved the purpose of reduce the data center tax from disaggregation using decoupled architecture. We have some detailed numbers in our POC experience before. And in our last year's talk, we talk about scale out multiple heterogeneous storage services. And particularly this talk is focused on the agility part. So another aspect we want to make sure that this work is also tied with how do we design SDS architecture to satisfy next generation storage media. So we want to encourage you to also dive into one of the other talk from our colleague called Mortimer, and we hope you can you have learned enough from this talk, as well as we have bring some new information based on our previous work. Thank you.
Thanks
Now,
all.
Arun and I think good for questions.